In this problem is given a half-wave antenna which goes from 0 till A, and there is a current written as like this. And the question is to find electric field in the radiation zone from this antenna. So if antenna receives a radio signal, then it electric field causes currents to flow in the antenna, and then alternatively charge two sides of it. Here is a representation of half-wave antenna. So this is wavelength, lambda, and this lambda is equal to 2a. Then a, the length of antenna is half lambda, half the wavelength. And about the current, it's 0 and 0, and 0 at A, and 0 at 2A. And it's alternating by sign. So to find the electric field in this antenna, we'll need to get help from pink pages. So first of all, there is definition of radiation zone. It's given for the length of the source point vector. And it's given for the length of the wave. So the following is limitations for the radiation zone of antenna, half-wave antenna. And then there is also written, so such dipole antenna current is written so there is some current amplitude and there is a time changing component is epsilon, epsilon cut exponential. And then the electric field can be found from dipole moment and dipole moment can be found from current. So the solution of the problem. The current is once again the amplitude of the current and the time changing component. So here in this problem, the part relating to the time change will be this cosine omega t. It contains the time t. So this will be the time. And the amplitude will be this part because it doesn't have a time changing component in it. And then the dipole moment. in Z direction. In the following way. Then integration used only the amplitude. In dz prime direction. So our dz, the length of antenna, is from 0 to 8. So what will change, what will be, so I0 is a constant, and the sinus will be minus cosine. I divided by A times change by I and times the from 0 to 8. Cosine phi. Um, Minus cosine 0. Here is 8 pi. So it will be minus 2 would be minus 1 and 1. And finally, that's what I get for the dipole moment. If it's correct, I lost 2, of course. Oh, 2A, 2 from here. Oh. Okay, I lost also minus here. And the formula is minus. So that's the dipole moment. From dipole moment, we can find the needed electric field. Electric field can be found as superposition of electric dipole radiation So that's the electric field in spherical system of coordinates with a big R. And first, so I will find this part, and the superposition of dipole moments is basically this part, right? Yes, it's just the sum of all of them. And we have here only one antenna. So, one dipole. For regarding this part, we have here Z direction. There is no Z direction in spherical system of coordinates, so I would transfer to spherical. So I will write here just the directions. So R cross Z and cross R again. So Z is bumping pages on the first page. No, perhaps second page. Yes, it's second page. Can be described as through the R and theta. That's the explanation, the transfer. And now cross product. So cross product R and R is small. So how is it? Theta, phi, and R. So cross product R and theta is phi. So minus sinus theta in phi direction. So that's what this part was. 0 and phi. And then times R again. Phi times R is again theta. So minus sinus theta in theta direction. That's what I got for here beside the constant part for the dipole moment. And now plugging it in here. Minus, I take over this minus, and then times theta in theta direction. This is first thing which first expression for the electric field, and then just let's see what is this big thing is. So omega and omega. First of all, taking a look at this part. If we take K, no, if we take omega out, we have here only T and then with a minus. We would have here T minus 2R divided by omega, right? And this part is called retardation time for electric field propagation in space. And then, of course, that also Also, speed of light is related to omega and k, which is a wave constant. And then this can be rewritten as E minus R divided by this c speed of light. And yes, this RT, this retardation time.